In this theorem, we are going to prove the following theorem, that every ideal of the integers is a principal ideal. But before we prove it, we need to review several tools that we need in order to prove this thing. The first one is just reviewing what a principal ideal is. The principal ideal generated by the element A is nothing more than the set of objects R times A, where R ranges over all of the elements of the ring that we are looking at. So in this particular theorem, the principal ideal generated by A is going to look like R times A, where R is ranging over all of the integers. And because multiplication is commutative inside the ring of integers, this can also be written as A times R, where R is an integer. And that, of course, is often written as A times Z. So this set here is just another name for A times Z. The second tool that we need in order to prove our theorem is something called the well-ordering principle. For the natural numbers. Now, the first thing that I want to remember is that the natural numbers themselves are the set of positive integers. And the well-ordering principle says that if we let S be a subset of the natural numbers and S is not empty, then S has a smallest element. And this is actually an axiom of the natural numbers. And if you think about this statement, it is more or less obviously true, which is part of why it's taken as an axiom. It is also, from a foundational point of view, logically equivalent to the principle of mathematical induction. The third tool that we are going to need in order to prove our theorem is the division algorithm. So I want to recall what the division algorithm says. The division algorithm says the following. If I let n be any integer and k is any natural number, then there exist unique integers q and r such that two things hold. The first thing is that n is going to be q times k plus r, and the second thing is that r is going to be trapped between 0 and k minus 1. In other words, r is actually inside the set 0, 1, 2, all the way up to k minus 1. And this is nothing more than the theoretical way of stating the long division algorithm that we all learned back in grade school. So now that we have our three tools lined up, I want to look at proving our theorem. So here again is the statement of the theorem, that every ideal is a principal ideal. So I'm going to start my proof with letting I be an ideal inside the ring of integers. Now, one thing I know about all ideals is either I is equal to the 0 ideal, or I is not equal to the 0 ideal. Now, if I is equal to the 0 ideal, then I is actually just the principal ideal generated by 0, and in this particular case, we have I is a principal ideal. So we need to focus in on this particular case. So we're now going to suppose I is not the 0 ideal. Well, the only way you can be not the zero ideal is to contain some non-zero elements. So there exists an A inside my ideal with A not equal to the zero inside the ring of integers. And let's see, what I know then is that A is an integer, so minus A is also an integer, and since I is a full-fledged ideal, and let's see, I need to make my writing just a little bit clearer. Since I is indeed an ideal, A inside I will imply that the additive inverse of A is also inside of I. And the other thing I know is I know that 1 of A and minus A is a positive integer. And that tells me that I contains some positive integers. And the well-ordering principle now kicks in and says that I has a smallest positive element. And we're going to let S be the smallest positive element in I. And what this says is it tells me that I know that 1, 2, all the way up to S minus 1, none of those integers belong to I. And that's going to actually be an important idea in just a minute. So I want you to make sure that you have this fact written down. So I want you to remember this. Now I'm also going to ask the question, is it possible that the principal ideal generated by S just happens to be I? And we're going to be investigating that idea, and we're going to be investigating it by doing a double inclusion proof. So we will show that this is indeed true with a double inclusion proof. So at this point, what I'm going to do is I'm going to let X be any element inside the principal ideal generated by S. Our goal is to show that X is inside the ideal I. That's what we need to show. Well, since X is inside the principal ideal generated by S, we know that X can be written as R times S for some R inside the ring of integers. But now look at this. I know that S is inside the ideal I, and I know that R is inside the ring Z. And so the definition of ideal says that that must be inside the ideal I by the definition of ideal. So we do know that the principal ideal generated by S is now a subset of the ideal I. Does the inclusion go back the other way? Well, let's look at that. Now let's let me let K be any element of I. Again, I want to remind you that the goal is to show that K belongs to the principal ideal generated by S. Now, what I know about K is this. Since K is inside I know that K will be an integer. And I also know that S is a natural number because S is the smallest positive element inside I. So of course it's a natural number. And now the division algorithm kicks in. So the division algorithm says there exist Q and R inside the ring of integers such that K is going to be equal to Q times S plus R, and R is trapped between 0 and S minus 1. And I want to think about this piece of arithmetic for just a minute. This is an equation inside the ring of integers, and I can manipulate it around. That particular thing is going to tell me that R can be written as K minus QS, and I also know that R belongs to the set 0, 1, 2, all the way up to S minus 1, because remainders, of course, are integers. That's up here. Now let's think about this for just a minute. S is inside I, and Q is inside Z. So this element here belongs to my ideal. And K also belongs to my ideal. So what I now have is that R is the difference of two elements in our ideal I. But ideals are subrings. That's enough to imply that R belongs to I. And of course, remember that R is inside this setup here. Well, what we've now got is this. R is inside the intersection of I and the set containing 0, 1, 2, all the way up to S minus 1. But that fact that I ask you to remember, I want you to remember it right now. None of these underlined guys are inside I. But 0 is inside I, and that's because I is a subring. All ideals are subrings, and the 0 inside the ring always belongs to the subring. Meanwhile, these elements are not in I, specifically because S is the smallest positive element of I. And so when we look at what we've got now, we know that R has to actually be equal to 0. And that says that K is equal to Q times S, and that says that K actually does belong to the principal ideal generated by S. And so what we've now done is we have shown that K belongs to I will imply that K belongs to the principal ideal generated by S. So I is now a subset of the principal ideal. And we previously had shown that the principal ideal is a subset of I. These two facts together say our ideal is indeed a principal ideal generated by its smallest element. This completes the proof, but I do want to make that particular observation very, very concrete. So, what we have actually shown is this important fact. If I is an ideal inside the ring of integers, then I is either equal to the principal ideal generated by 0, or I is equal to the principal ideal generated by S, where S is the smallest positive element of the ideal I.